Okay, hi, so welcome to the video on Chemistry Unit 3. So this is a whole Unit 3 paper from May 2014. It is the higher tier paper, so if you're doing foundation tier, then some of this won't apply to you. But we're going to go through the whole paper, and as usual, if you do struggle to keep up, please feel free to pause, rewind the video, and go at your own pace. Alright, so let's have a look straight away at question 1. So, wait, slightly too far. It says that water in Britain is taken from reservoirs to use as drinking water. And in 1A, it says, what are the two main steps used to treat water from reservoirs? And give one reason for each step. So we need two reasons and, two steps and two reasons, which is going to give us 4 marks in total. Now, if you're not familiar with this topic, please do have a look at my videos on water treatment. But the first one that we're going to do is we're going to filter the water. So I'm going to say filter water. Right, that's 1 mark already. That's a step. And why do we filter the water? Because basically when you filter something, you're putting it through almost like a sieve, and those that filter paper or the filter, whatever it is that you're using, is going to stop large particles from getting through, and so it removes solids from your water. So this is to remove solid particles from water. And obviously, if you're thinking about water from a reservoir, those particles are most likely things like dirt and sand or whatever, which is found at the bottom of the reservoir. Alright, so what else do we do? Well, the second point is going to be adding chlorine. Right, not like in a swimming pool, we don't add anywhere near as much chlorine as that, but it serves the same purpose. Chlorine is added to kill or remove microorganisms. Alright, microorganisms, I'm going to put in bracket there, bacteria, because they're the most common. So chlorine will actually kill them, and that means that we're not going to get any nasty infections from the water. Alright, and that's good for 4 marks. So let's move on. We've got question 1b. Some people use water filters to treat water before they drink it. Water filters remove hardness from hard water. What is in water filters that removes the hardness? Alright, and so what it is that's going to remove the hardness is an ion exchange column. Ion exchange column. And that is enough for the 1 mark. Now, the reason why this removes hardness from the water is because hard water, be it temporary or permanent hard water, remember there are 2 types, contains ions. One will be calcium sulfate and the other one will be calcium hydrogen carbonate. So calcium sulfate is permanent and calcium hydrogen carbonate is temporary. Alright, and if we can exchange those ions for other ions using the column, then we remove the hardness from the water. So in 1b, it says suggest why water filters are used in the home, or suggest why they contain particles of silver. Alright, now silver basically stops the growth of microorganisms. So silver prevents microorganisms, so obviously mainly bacteria, but other ones as well, from growing. Alright, so chlorine is used to kill microorganisms and silver stops them from growing. Alright, so 1c, it says pure water can be produced by distillation. Why is it not an economic method of treating water for drinking? Right, well, distillation, basically you have to boil the water and then condense it again, right? So that's going to require a lot of energy, and if you had to do that for all of your water, then it'd use loads of energy. So it requires too much energy, and so not cost effective. Alright, I'm going to put in brackets here, expensive. Okay, next we've got 1d. It says drinking hard water has health benefits. State one health benefit of drinking hard water. Now, hard water contains calcium, as we've already said. And so what are the health benefits of taking calcium? Well, they're good for your bones, they're good for your teeth, and it's also been said that they are helpful for other conditions such as heart disease. Alright, but the easiest one is I'm going to say helps maintain strong and healthy bones. Alright, because that is a very common benefit of calcium. Alright, and so that is the end of question 1, because it says turn over for the next question. And there we go. So let's have a look at question 2. It says the structure of an alcohol is shown in figure 2. And here we see that alcohol. If you can name it, this is actually ethanol because we have 2 carbons. Alright, it says draw a circle around the functional group in the structure of alcohol. Now remember, if we just have carbons with hydrogens, this is going to be an alkane. If there's a double bond, it's an alkene. The thing that makes this an alcohol is the fact that we have this group on the end, which is an OH functional group. Alright, it says what is the chemical name for this alcohol, and I've just mentioned it. 2 carbons means it's ethanol. Alright, 1 carbon would mean methanol, and 3 carbons propanol, and so on. So, easy enough. Question 2b says alcohols are used as fuels. A student plans an experiment to find the energy released per gram of alcohol burned. The student uses the apparatus shown in figure 3. Alright, so let's have a look here. We have a thermometer, we have water and a glass beaker, and we've got an alcohol burner underneath, so we're heating the water up and we're seeing how much the temperature rises. Suggest 2 ways that this apparatus could be improved to obtain accurate results. Now, there are a fair few here. There are a fair few things that this student has clearly done wrong. The first one is this here, the glass beaker. We don't use a glass beaker in experiments like this because we're trying to heat it up. We're trying to heat the water up. Now, we need, therefore, something which is a good conductor. And a good conductor is, of course, going to be a metal container. So rather than a glass beaker, we're going to use a metal calorimeter. Alright, because a calorimeter is basically a fancy word for the apparatus we use to measure the amount of heat that's applied to something. Alright, so we're going to say replace the glass beaker with a metal calorimeter. Alright, now on the same note, as we don't want to lose any heat, right, we can see here that this glass beaker is open. It's open at the top, which means that immediately as you're heating the water is also going to be losing heat to the surroundings. We want to keep that heat in as much as possible. So I'm going to say use a closed lid on the calorimeter. Right, because that will stop heat escaping. Now, that's already good for 2 marks, so we're going to stop there. We could have also said that you do it in a container which keeps a draft out, because if you have a draft, it takes heat away from your apparatus. We could also have said that we stir the water just so that it's even all the way through. So there are a few different answers that we could have had for this question. Alright, and then so 2b, part 2, says, in this question, you'll be assessed on your use of English. Describe how the student should do this experiment. You should include any measurements the student make. Do not describe any improvements to the apparatus, and do not describe how to do the calculations. Alright, so I'm going to go back up to the apparatus quickly, just so I can describe what we're going to do with the diagram there. So let me rub out these arrows. What we're going to do is we're going to burn alcohol, right? We're going to burn alcohol, and obviously we are going to see how much this raises the temperature of the water. Now, what's important is we need the mass of water, right? Because even though in this question we're not asked to talk about the calculations, we know that down the line you are going to need to do some calculations if you're going to use the data, if the data is going to be useful. So we need the mass of water, all right? We also need the mass of alcohol, all right? So the mass of alcohol. We are going to burn the alcohol, right? And that means that the mass of the alcohol is actually going to go down. So we need the final mass of alcohol. We are going to also need the initial temperature. I'm just going to put T there, of water. And we're going to need the final temperature of water. right? Because we need to know how much the temperature changes, right? The equation that we actually use is Q is equal to M times C times by delta T. M stands for the mass of the water, right? Delta T stands for the change in temperature, and C stands for the specific heat capacity of water. Now that's not something we need to measure, that's something we know, right? You don't need to know what it is, it's actually 4.2. But we're not asked to actually describe this part in our question, but this basically explains to you why we need all these things. Now, why we need the mass of alcohol is because at the end, we're going to get an amount of energy, and we can then say it's X amount of energy per gram of alcohol, or X amount of energy per mole of alcohol, right? And so therefore, we need to know how much alcohol was used. Alright, so I think that's enough for now. Let's go and actually get this on paper. So, the first thing that we are going to do is we are going to measure the mass of water, H2O or water. Okay, measure the mass of the water. We're also going to measure the initial mass of alcohol. All right. So after the apparatus has been set up, we can then measure the initial temperature of the H2O. All right, we're then going to carry out the experiment. So we then burn the alcohol. All right, so we burn the alcohol, and after a period of time, extinguish the burner. All right, because we don't necessarily want to burn all of it. We burn an amount of it, and after a period of time, or after we've reached a certain temperature that we wanted to reach, then we can extinguish. Okay, so then we measure final temperature. All right, and from that, obviously, we would work out the temperature difference, but it clearly says we don't describe with the calculations. So we measure the final temperature. We're going to measure the final mass of alcohol. All right, and then that will allow us to work out the change in mass of our alcohol. All right. So I'll actually just put it in brackets here so you know why we've done it. So from the final temperature, we can work out delta T, which is temperature difference. And from the final mass of alcohol, we can work out change in mass of alcohol. All right, and then that is basically the end of the experiment. So you have the temperature you want, you have the mass that you want, okay, and that is basically how we do it. And then we can work out the amount of energy released and the amount of energy released per mole or per gram of fuel from there. All right, and that is perfectly fine for 6 marks as long as you do it, as long as you write it in good sentences. So in question 3, we are told that in 1869, Dmitry Mendeleev produced his periodic table of elements. Mendeleev placed the alkali metals in the same group. What evidence did Mendeleev use to decide that the alkali metals should be in the same group? Now, back then we didn't know about the electron configurations, but he could say that they were in the same group because they had similar chemical properties. Okay, right, so similar chemical properties, because they react with similar compounds in similar ways, so their chemical properties are very similar. B, it says describe how the elements in the modern periodic table are arranged. Part 1 in terms of protons. So they are arranged in ascending order of proton. I'm going to put in brackets here atomic because they're the same thing, atomic number or proton number. Alright, so starting from 1, which is hydrogen, and all the way through. Now part 2, sorry, it says in terms of electrons. Now this could actually be confusing because number of electrons is equal to the number of protons, so it is actually exactly the same trend. That is perfectly true when the elements are atoms, but not when they are ions. Alright, so what I'm going to actually say is that they are placed in groups with same number of electrons in outer shell. Alright, I chose that because it's different to the proton answer, and it's still true. You would have actually got the mark by saying in ascending order of number of electrons. Alright, because both trends are completely true, you would have had to be given the mark for both, but I would rather give the alternate answer to the one we gave before. Alright, so 3C, it says state 2 properties of transition elements that make them more useful than alkali metals for making water pipes. Alright, now the alkali metals are notoriously soft, alright, whereas the transition metals, a lot of them are very hard because you're looking at things like copper and iron. So, transition metals are stronger than the alkali metals. Alright, that's one mark. Now next, well, the alkali metals are actually the most reactive metals in the periodic table, and if you put water in them, they all react with water. Potassium, for example, will explode if you put water in it. Sodium and lithium will fizz and bubble, and they will react violently with water, so not very good for water pipes. Transition metals are notoriously way less reactive. Iron and copper and things like that, they're not very reactive. If you look at things like gold and platinum, they're not reactive at all. So, transition metals are less reactive. Alright, and that's good for 2 marks. Let's carry on. It says in 3D, describe and explain the trend in reactivity of the alkali metals in group 1. Alright, now when it says describe and explain, obviously first we have to describe. So what is the trend of reactivity down the alkali metals? So reactivity increases down the group. Alright, lithium is at the top of the group, and then sodium, and then potassium, but we know that potassium is highest on the reactivity series. Alright, so now we need to explain this. Well, if you think about the structure of the atoms, right, lithium only has 2 electron shells. So its outer electron, which is its third electron basically, is very close to the nucleus. Now the electrons are all negatively charged and the nucleus is positively charged. And because that electron is close, then it feels strong attraction to the nucleus and it's harder to pull away. Now when you go down the group and you think of something like potassium, let me just draw a quick sketch. So you've got the first shell, right, which has got 2. Then you've got the second shell, and this would be lithium, just 1 electron in there, right? But in potassium, this is full up. And then you've got the third shell, which in potassium is also full up. And then you've got the 4th shell, right? And now if we just focus on this electron here, this electron is way further away from the nucleus than this electron, right? And so it's feeling less force of attraction from the nucleus than this one. Now there is an argument. You might say, well, in potassium the nucleus is more positively charged. Now that's very true, and the reason why this is cancelled out is electron shielding. So the nucleus is actually shielded by these inner electrons. So these inner shells shield some of the positive charge from the outer shells, which means that they're not affected as much. And so these electrons at the end, they are easiest to pull away because they feel less attraction. Alright, now we don't actually have to go into that much detail. Okay, you can do, of course you can, but we don't need to. So what I'm going to say is that outer electrons are further from the nucleus as we move down the group. Alright. Now what this means is that the outer electrons feel less attraction to the nucleus than the inner electrons, and therefore they are lost more easily. I'm put in brackets, less difficult to remove, which equals more reactive. Alright, and that would be perfectly fine for 4 marks. Now, when I've said the outer electrons are further from the nucleus, right, I've then said that the outer electrons feel less attraction. You could say that that is a result of electron shielding, which is what I mentioned before, and you'd definitely get marks for that, but it's not absolutely required, right? That is higher level stuff, and you're not required to go into that level of detail. Okay, right, and that brings us to the end, I believe, yep, of question 3. So question 4, it says that hard water causes scales in kettles, as shown in figure 4, right, that's true. Acids are used to remove scale. It says give the name of a carbonate in scale. Right, now we know that scale is caused by calcium carbonate and magnesium carbonate, so either one of those is going to be correct. I'm just going to say calcium carbonate. Alright, good. Part 2, it says when acids react with scale, a gas is produced. What is the name of this gas? Well, the clue is in the word carbonate. Alright, because we have a carbonate, we have carbon that needs to be removed, and that leaves as carbon dioxide. So the name of the gas is carbon dioxide. Easy enough. In 4b, it says ethanoic acid is used to remove scale. Complete the displayed structure of ethanoic acid. Right, and we know that ethanoic acid is CH3COOH. Now, an acid group is a carbon doubly bound to an oxygen and also singly bound to an alcohol group. So I'm going to have a double bound oxygen and a singly bound alcohol group, and that is the displayed formula. Alright, simple enough. Let's move on. We've got 4c. A student compared the rates at which ethanoic acid and hydrochloric acid react with scale. Both acids had the same concentration, right? Remember, that's not pH, that's concentration. The student found that hydrochloric acid reacts faster than ethanoic acid with scale. Explain why hydrochloric acid reacts faster. Now, this is why I said that pH is not the same. Hydrochloric acid is a strong acid. Ethanoic acid is a weak acid, all right? So I'm going to say that hydrochloric acid is a strong acid, but ethanoic is a weak acid. Now, a strong acid means that it fully dissociates into its ions, whereas a weak acid means it doesn't. So HCl, right, I'm just going to shorten hydrochloric acid, fully dissociates into its ions, which means more ions to react with the scale. Alright, and that is more than enough. Alright, so in C part 2, it says hydrochloric acid should not be used to dissolve scale in kettles, and suggest why. Well, you'd be tempted to say, well, we don't want to drink hydrochloric acid, right? But it hasn't told us here that we're going to drink from the kettle straight after, so that's actually not going to be an answer. The reason why we shouldn't use hydrochloric acid is because it's such a strong chemical. It's a corrosive chemical, and that means it's actually going to start to break down the heating element in the kettle. So I'm going to say HCl is corrosive. All right, and therefore I've spelled corrosive wrong, haven't I? It's only one S, and can break down heating elements. Ooh. There we go. All right, so for D, a student does a titration to find the concentration of a solution of hydrochloric acid. The student titrates 25 centimeter cubed of HCl with sodium hydroxide solution of concentration 0.2 moles per decimeter cubed. The equation for the reaction is this, and we have the equation here. The student added 28.6 centimeters cubed of sodium hydroxide to neutralize the hydrochloric acid, and it says calculate the concentration of hydrochloric acid. Now, in these equations, the first thing you want to do is have a look at the molar relationship from the equation. So if we go up here, we can see that one hydrochloric acid will react with one sodium hydroxide. That's cool, it makes things easy for us. So we have a 1-to-1 ratio, and that's what I'm going to write here in brackets. All right, if it was, for example, two sodium hydroxides, right, then it would be a 1-to-2, and we'd need to multiply or divide when we come to our question. But it's a 1-to-1, that's fine. So what we need to do is we need to equate the numbers of moles, right? Not the concentrations, not the volumes, the numbers of moles. Now, number of moles is equal to concentration times by volume, all right? And so let's say, for example, for HCl, N equals CV, and for sodium hydroxide, N equals CV. Now, if these numbers of moles are the same, then what we can say is that concentration times volume of hydrochloric acid is equal to concentration times volume of sodium hydroxide. All right, let me just rub out these at the top. And there we go. And now we're just going to fill in the numbers. So what do we have? Well, we know that, I'm going to say this is HCl and this here is NaOH, just so we're clear. We know that we have 25 centimeter cubed of hydrochloric acid. All right, that's the volume of hydrochloric acid. Now, I always prefer to write in decimeters cubed straight away because, look, we want moles per decimeter cubed. So to convert 25 into decimeter cubed, we divide by 1,000, which is 0.025 decimeters cubed. All right, let's make that slightly bigger. There we go. Is equal to concentration. Remember, that was 0.200. So 0.200 of sodium hydroxide from there. And the volume of sodium hydroxide was 28.6, so that's times 0.0286. All right, now this doesn't look too nice, but for us to get concentration on its own, all we need to do is divide by 0.025. So I'm going to divide both sides by that, and do the same to this side. All right, so I'm going to get concentration is equal to this, what we had on the right hand side, all divided by 0.025. That's going to give me an answer of 0.2288, or to three significant figures, 0.229. All right, and so let's just rub this out so I can write my answer. My answer is 0.229. You could have said 0.23, you could have said 0.2288. That all just depends on how precise you want to be, but this is the correct answer. All right, so let's move on. All right, so in question 5, it says, in 1909, Fritz Haber invented a process to produce ammonia from nitrogen and hydrogen. That's true, the Haber process. Complete and balance the chemical equation for the production of ammonia from nitrogen and hydrogen. All right, well, ammonia, you should know, is the chemical NH3. Right, now we don't have state symbols here, so we don't need to write in state symbols. Now all we need to do is balance this. Well, we have 2 nitrogens on the left-hand side, and we have how many hydrogens? 1, 2 times 3 makes 6. And so if we need 2 nitrogens, we straight away know that we're going to double the amount of ammonia. And we can see that that also satisfies the hydrogens, so that is done. Alright, so let's move on. 5b, that's too far. There we go. Figure 5 shows how the equilibrium yield of ammonia changes with pressure at different temperatures. Alright, so you can see all these lines represent different temperatures. Alright, we have a percentage yield of ammonia, and we have the pressure on the x-axis. Alright, so it tells you at different pressures how much the yield is going up. Okay, so B part 1. The temperature on the graph that gives the highest yield of ammonia is, well, we can see that the highest yield is this graph here, which is the 200 degrees Celsius graph. Alright. B part 2. It says the temperature used in the Haber process for the production of ammonia is 450 degrees Celsius. Why is a temperature much lower than 450 degrees Celsius not used in the Haber process? Alright. Now, yes, the yield is going to be higher at low temperatures, but temperature, remember, is also related quite heavily to the rate of a reaction. And if you reduce the temperature by a lot, then the rate of the reaction goes down. So even though the yield is high, how long it takes to get that amount is going to be a long time. So what we're going to say is that rate of reaction will be too low. Alright, and so that is part 2. Let's carry on. I've got part 3 here. Use the information in figure 5 to answer this question. Draw a ring around the pressure that gives the highest yield of ammonia. So let's quickly look back at the graph. Here we go. Now we're looking at the pressures now, and we had pressures between 100, 200, and 400 for our pressure. All right. So all we need to do is have a look at the graph and say which pressure gives the highest yield, and you can clearly see that the pressure, as the pressure goes up, the yield is going up, right? That's for every graph, even though, you know, it flattens off and it starts to go up slower. The highest yield is going to be for every single graph at 400 atmospheres. All right, so I'm going to go down and I'm going to draw a ring around 400. It says in part 4, the pressure used in the Haber process for the production of ammonia, all right, is 200 atmospheres. Why is a pressure lower than 200 atmospheres not used for the Haber process? And you've got to be really careful here. It's trying to trick you. It says, why is a pressure lower than 200 atmospheres not used for the Haber process? Well, that's because below 200 atmospheres, as we saw on the graph, the yield is too low. And so below there, we have a low yield. All right. What you might be thinking straight away is that the question was going to ask, why don't we use 400? But it actually says, why don't we use a pressure even lower than 200? All right. So you've got to be really careful and read the question there. In 5C, we're asked, how is ammonia separated from unreacted nitrogen and hydrogen in the Haber process? All right, now what happens in the Haber process? You should have studied this. If not, then have a look at my video on the Haber process. The gases are cooled, right? There's a cooler which cools the gases. And I'm just going to say to a low temperature, just so we're clear. All right, ammonia will condense. Right, in brackets, if you want, you can say liquefy. Whereas nitrogen and hydrogen remain as gases. All right, so we separate the liquid from gas. All right, pretty simple. Basically, nitrogen and hydrogen have a lower boiling point than ammonia does, and so we can turn ammonia to a liquid where nitrogen and hydrogen are still gases. And that does it for question 5. Alright, so question 6 says that some cars are powered by hydrogen fuel cells And it says, what type of energy is released by hydrogen fuel cells? Now, hydrogen fuel cells are one way of powering electric powered cars. All right, so the type of energy they release is electrical. All right, the type of energy that is converted into electrical is going to be your chemical energy, but it's converted into electrical. All right, so 6b, it says, owners of cars powered by fuel cells buy hydrogen from hydrogen filling stations. Figure 7 shows how the number of these filling stations in the UK is expected to increase up to the year 2030. All right, and then we've got the graph here. We've got expected number, and we've got the year on the bottom. All right. Now, let's move on to the next page for the question. It says, use the information in figure 7 and your own knowledge to answer the question. Suggest 2 reasons why the UK government might encourage the building of more hydrogen filling stations. All right, now you should know, let's just scroll down slightly. You should know that hydrogen fuel cells are not going to produce carbon dioxide, which is one of their main benefits. So, the first thing I'm going to say is that hydrogen fuel cells do not produce CO2, and so less pollution. That's certainly one reason why we want to use hydrogen fuel cells and not the current fossil fuels we're using. Another one, bearing in mind that they're fossil fuels, is that they are running out. All right, so fossil fuels, I put in brackets, petrol, diesel, are running out, and so we need to invest in alternatives. All right, okay, so let's move on to the next page. Here we are. We've got 6c, which shows the equation for the reaction of hydrogen with oxygen. All right. Now it says, during this reaction, energy is used to break the bonds of the reactants. Energy is released when new bonds are made to form the product. Bond energies for the reaction are given in table 1. All right, and we're showing the structures of hydrogen, oxygen, and water, just in case you don't know. It says, calculate the energy change for the reaction. All right, so in this question, basically, we need to think about the energy we're going to add in. Obviously, you add energy to break bonds and the energy released when bonds are made. So the bonds that we're going to break, well, we have hydrogen gas, all right, but we have 2 of them. So what we need is we need 2 lots of the amount of energy that we supply to break those hydrogen bonds. So we put in 436 kilojoules of energy, but we do that twice because we're breaking 2 of them. So it's 2 times 436, all right, plus, well, there's only 1 double bond in oxygen, so it's 1 lot of 498 plus 1 times 498, all right? Now these are the reactants, so this is the amount of energy that we put in, all right? And then the amount of energy that we then release is going to be 464, okay, because that's the energy in an oxygen-hydrogen bond. But we have 2 of those bonds in water, and we have 2 waters, so it's 2 times 2 makes 4 of these. So we're going to release, so take away, 4 times 464, and that is going to give us our total energy change. And that will give us an answer of negative 486 kilojoules. All right, and that is our bond, or that is our energy change, sorry, for that reaction. All right, they would have given you the reaction if you'd have said positive 486. Either way will do. But negative 486 is more correct because this negative symbol shows you that in total energy has been released in an exothermic reaction. All right, so I always prefer to do the amount of energy supplied, all right, to break the bonds, take away the amount of energy which is released, which will give you this negative answer. All right, and so that is the end. There we go, we had an answer box, and that is our amount of energy. So now we've got C part 2. The reaction of hydrogen with oxygen is exothermic. Complete the energy level diagram for this reaction on figure 9. Alright, clearly label the activation energy. Alright, so if we're reacting with oxygen, that means that, if we're reacting to form water from oxygen, okay, in a reaction that's exothermic, it means that energy has been released, which means that the products, or water, is going to be at a lower energy than the reactants, because energy has been given off, alright? So the first thing I'm going to do is I'm going to draw a line here to show that the products are lower down than the reactants, and this is going to be 2H2O, alright? So this is the balanced equation. Now, I'm not just going to go, well, let's first change the color, just so you can see that this is energy change. I'm not just going to go like this and say, there we go, because there is an activation energy in order to allow this reaction to occur. That means we need to supply even more energy for this to then react. So what we're going to do is we're going to show this curve, which I'm sure you've seen before. All right, well, let's make it slightly more pronounced, maybe like this. All right, and the activation energy is the extra amount of energy that you apply. So this here is the energy on top, which you have applied for then the reaction to occur. So that there is the activation energy. Activation energy. Sometimes you see that as EA. All right, now that's the end of question 6. So let's now move on. Alright, so in question 7 we are told that the colours of fireworks are produced by chemicals. Alright, information about 4 chemicals are given in table 2, and we're asked to complete table 2. Right, so what we have here are colours produced in the firework and the chemical that causes those colours. Right, this might seem a bit confusing, but it's basically the flame test. Right, we have had a look at the different tests for different ions, and the flame test is one of them. Right, you'll notice that barium gave you green. Right, and barium chloride here is giving you a green colour. All right, calcium gave you a red colour, and you'll notice that calcium sulfate here is giving you a red colour in the firework. Now this tells you that the flame test colours are what we're after. Now which chemical is going to give us our crimson colour? Well, that is actually lithium. All right, lithium is going to give us our crimson. And then lastly, we are given sodium nitrate. And what colour does sodium give on the flame test? Well, it's sort of a yellow-orange, and so I'm going to say orange in there. You would have been given the mark for yellow as well, but orange is perfectly fine. All right, so let's move on. In 7b, we are asked to describe a test to show that barium chloride contains chloride ions and give the results of the test. Alright, and this is of course the halogen test, and the halogen test is where you add a solution of silver nitrate. It's actually ammoniacal silver nitrate, so it's dissolved in ammonia, but we are fine in saying silver nitrate solution. So silver nitrate solution is added. Alright, and well, what's the result? Well, if you have chloride ions, you get a white precipitate. If you have bromide ions, you get a cream precipitate, and if you have iodide ions, you get a yellow precipitate. In this case, we want chloride ions, and so a white precipitate will be our result. Precipitate if chloride present. Alright, and that's easily worth 2 marks. Next, 7c, it says a student did 2 tests on a solution of compound X, right? So it looks like we're going to have to find out what the compound is. Test 1, sodium hydroxide was added and a blue precipitate was formed. Test 2, dilute hydrochloric acid was added, barium chloride solution was then added, and a white precipitate was formed. The student concluded that the compound is iron 2 sulfate. Is the student's conclusion correct? Alright, so let's have a look at the 2 tests, and we can actually decide what the results mean. So test 2 to start off with, if hydrochloric acid and then barium chloride is added, this is the sulfate test. Alright, the sulfate test. And the white precipitate means yes, we have sulfate ions. So we can say that we probably do have a sulfate. Alright, so sulfate ions is correct. Now the sodium hydroxide test, alright, now that is a test for metal ions. Now this will give different colours depending on the metal. For example, aluminium is going to give you a white colour. Alright, iron actually gives you a green colour. Alright, iron 2 anyway gives you a green colour. Iron 3 is going to give you a red-brown colour. The blue colour is formed from copper 2. So this actually tells us that we probably have copper 2 plus ions, not iron 2. Alright, so where it says explain the answer, the blue precipitate from test 1 is a result of copper 2 plus ions, not iron 2 plus ions. Alright, the white precipitate in test 2 indicates sulfate ions. Alright, and I'll just put in brackets the formula, which is SO4 2 minus. Fe 2 plus ions in test 1 would produce green, let's just go down, precipitate. So X, or so let's say that student is incorrect, and I might even say X equals copper sulfate. Alright, and then that is more than enough for those 3 marks. And that actually brings us to the end of this test paper. So I hope you were able to follow that. We did go through fairly quickly, so feel free to go back, rewind, pause the video as you wish. But I hope that's helped, and if you do have any questions, please feel free to post in the comment box below, or to send me a direct email using the link. I'll be sure to get back to you. But please remember to like and subscribe, as there are plenty more videos like this coming up very soon, and I look forward to seeing you in the next one.